The goal of today's notebook, or should I say the lecture, is to perform classification. In the last notebook, we turned audio into features. I will show you the Excel file that has all the extracted features. So basically today we will feed this Excel file into our models. That means that today we give the computer our decision making brain. We will load a feature table as shown, then we will split it into train test. We will fit multiple models. We will evaluate with accuracy, precision, recall, F1, and visualize confusion matrices, and finish with a McNemar test to check if a model is truly better, not just lucky, on this split. So first, what we do is load our features file. The Excel file is a row per frame or aggregated window with columns like SCN, SCR, etc. plus a class label. Now what we do is we separate our features from our labels. X now is the numeric feature matrix and Y is the label vector. Then again, what we do is that we train and split test features. Here you can see that we are training on 70% of the data and we will be testing on 30% of the extracted features. And then comes our models, machine learning models. So I will simply briefly give you an overview of each of the model. What does linear discriminant analysis do? It draws a straight line that is a hyperplane between different classes, and it is fast and interpretable as compared to other models. If we look at the KNB, it basically applies Bayes rule per feature. And what is surprising is that it actually does quite good on noisy data. If we look at the decision tree model, that is the fine tree, it will define rules like if spectral centroid is greater than 900 and flux is greater than 2000, then it is asthma. It basically tries to define rules like such. Then we have find canon. So what this particular canon does, it picks the nearest neighbor. It is very sensitive and it has high variance, but it can be great when features are very informative. If we look at Subspace canon, which is mentioned here, it is actually a smoother version and gives vote, basically nearby points, vote gets more preference. Now about the bagging tree, many trees on bootstrap samples. So basically it has many trees on bootstrap samples and average predictions and lower variance. So typically it is also quite strong. And then we have different versions of support vector machine, which for the time being I have commented out. So first of all is accuracy. Accuracy is the overall fraction correct. Thus, how accurate your model is performing on all over your data. But it can be quite misleading if it is imbalanced data. Precision is the average of per class. When I say asthma, how often am I right? So this is what precision will be telling us. Recall is the average of per class sensitivity, meaning when I say when the case is asthma, how often do I catch it? It is recall. And F1 is the harmonic mean of precision and recall per class. Then it is averaged, and if balance misses versus false alarms. Then we are also computing type 1 and type 2 error per class. Let me explain what type 1 and type 2 errors are. Type 1 is basically false positive rate. How often we raise a false alarm for each class. Type 2 false negative rate. How often we miss the class. And if we see it from medical lens, missing pneumonia. So here pneumonia is false negative, and missing pneumonia can be dangerous. So we need to keep type 2 low. Overcalling asthma. Asthma is false positive. We also need to keep it low. Why? Because if it is high, then our type 1 would be high. And then obviously we are showing the confusion matrix report, which will give us the overall view of each one. Let's look at the result. What happens if we feed our Excel file and train our models on them? As I mentioned earlier, we divided 70% of data to be fed into the models as training data and the rest 30% as testing. So 70% of data is equivalent to 14,000 samples, and the rest of the 30% data is equal to 6,000 samples. Why is this important? The training set teaches the models, and the test set, which the model never sees during training, tells us how well the model generalizes to unseen lump sum data. So everything you see from now on is true generalization performance, not just the memorization of each model. In particular case, let's look at the linear discriminant analysis, linear discriminant model. And as defined earlier, linear discriminant is a linear classifier. It tries to separate classes with straight lines in feature space. And if we see the confusion matrix here, it predicts asthma very strongly. 2000, so 2900 something samples are exactly identified asthma as asthma, but it struggles with normal because many normal cases get misclassified as asthma. Pneumonia is also partly confused with asthma. So the general interpretation would be asthma dominates because its spectral features may align more strongly with the linear separation, but the real-world diseases are non-linear, which is why linear discriminant underperforms. If we talk about kernel Naïve Bayes, this looks very different. Why? Because KNP heavily misclassifies many asthma patients and predict them as normal. Normal also gets confused with asthma. Why is it behaving like this? Because Naïve Bayes assumes all features are independent, but our lung sounds features are highly correlated. Remember the previously plotted heat maps? That assumption breaks down, so KNP struggles. Pine tree. Now this is impressive. Nearly all asthma cases are correct. Normal 1283 are exactly correct. The pneumonia 1357 are again exactly correct. Also well separated. And we see very few off-diagonal errors. Why is it behaving so good? Because decision trees partition the feature spaces into flexible regions. Our spectral features, that is centroid, entropy, roll-off, are non-linear and threshold-like, and trees are perfectly suited for them. That's why pine tree is emerging as the best model so far. Gaussian Naïve Bayes. This is basically the same pattern as KNB. It has strong overlap between classes, many asthma and normal Wheeze classifications. Again, because of feature correlation, Gaussian MB cannot handle the complex relationship among some features. Fine Canon. Here's Canon with just one neighbor. Asthma classification is again quite strong. Normal and pneumonia are decent but weaker. But still it outperforms Naïve Bayes. Why? Because Canon works by looking around in the feature space. With fine Canon, k is equal to 1. It memorizes training samples. This helps in cases like ours where disease cluster tightly. And the downside is noisy samples can mislead it. That's why the error remains. Backtrees. Backtrees combine many decision trees. An ensemble. This is even cleaner than pine tree. Why? Because ensembles reduce variance, where a single tree might overfit bagging averages across 50 trees. That stabilizes predictions. This is why BT rivals are even beats FT. Subspace Canon. This variation of Canon-based distances and uses multiple features, subspaces. Performance is better than fine Canon, but not as good as trees. It captures more global structure, but still struggles with overlapping disease features. Canon is in the middle ground. Here's the summary table with accuracy, precision, recall, and F1. If we see this particular table, we can see each model's ranking. Linear discriminant, the accuracy is almost 0.63. It is an average model. If we look at KNB and GNB, both have around 43% accuracy, which is very poor. Then again we have pine tree. Its accuracy is 0.97, which is quite understanding. 0.975 actually, to around about 98 we can say. And BT accuracy is exactly 98.22, in middle of 98 to 95%, and SKNN accuracy and FKNN, both of them are 85. Good but not perfect. So overall, if you see that FT and BT stand out as winners. Now if we look at the accuracy bar chart, models shoot up near the top, that is FT and BT. Naïve Bayes variance lag behind, while KNN sits in the middle. So this visually instantly tells us which models are reliable. Accuracy alone can be misleading if classes are imbalanced. That is why F1 score is critical. Here again, FT and BT dominate. FKNN and SKNN are decent, LT is moderate, and Naïve Bayes is poor. So across both accuracy and F1, FT and BT are the consistent leaders. Now let's see the statistical significance with McNemar's test. High accuracy alone doesn't guarantee that one model is truly better than another. So to test whether the difference in performance is statistically significant and it's not just a random choice, we will use McNemar's test. So basically how it works, we compare each classifier directly against the best variant. In here we have FT and BT. And we will be basically counting two variables. One, that our case's competitor is correct but FT is wrong. And the second is that the model that is performing the highest is correct but competitor is wrong. So if both variables and both models perform similarly, both variables would be equivalent. And if the models are statistically different, then the values of B and C would differ significantly. So this is how we perform McNemar testing. And here are the results. So don't mind, there here basically we are competing actually against the FT, not SCM. And let's summarize everything. So Naïve Bayes, both KNP and GNP, they perform poorly. And if we see LD versus FT, it gives us a significant difference. KNP versus FT, again significant. GNP versus FT, significant difference. FKNN versus FT, again significant. But BT versus FT, because both of them as previously have around about 98% accuracy, have significant, but the p-value is 0.00001, and this is the closest competitor. So FT basically the strongest model, but BT come close. So that's how FT is the ultimate winner. Now let's just visually see that whether which one is significant or not, and how our tests are performing. And we are only able to get a very good strong p-value against BT. But yes, they are competing again, and the rest of them are not quite good. Now let's just summarize. We train multiple models, and among them Naïve Bayes, both KNP and GNP, they perform poorly. So here they are weak models. The moderate models are linear discriminant, FKNN and SKNN. They are okay, but they are not giving us state-of-the-art accuracy. Now the strong models are FT and BT, because they both dominate accuracy in F1. And in significant testing, FT significantly outperformed all others, while BT has the closest rival. So if we had to pick a single classifier for deployment on lung sound analysis, FT, that is fine tree, would be our choice. And that concludes our deep dive into the classification results. So this experiment basically shows how machine learning plus signal processing can provide meaningful insights for biomedical applications. Now have a complete workflow: preprocessing, feature extraction, and classification. And as I told earlier, in the next stage we can explore the deployment, turning these trained models into an application or a clinical tool. And we will also deep dive into deep learning models for automatic feature extraction. Any confusion or any queries regarding the code implementation or any step that you are not exactly able to understand, so do comment, and I will also share the link of this notebook. Do subscribe. You have to go, as I will be uploading the next part very soon. Bye.